Okay, so today we are going to do motional EMF and we are going to do something called eddy currents. Okay, so not a very difficult topic, but important. Okay, because questions are asked from these topics. Okay, so I will try my best to make you understand. Okay, what is going on. So let's start. Okay, so see, we'll start with your motional EMF. Let me check how many of you are. Only 9 today. Ish. Mhm. Okay. Anyways, we will start. Okay. So those who are right now not here. Okay, Beauty has joined. Good. Mm, Malan is joined. Okay. Okay. So we will proceed. Okay. So okay, let me just wait for 2 minutes. Okay, guys. Any idea about embossed pattern, guys? Embossed pattern. CBSE, I saw. Okay. Some changes are there for CBSE pattern. What about emboss? Emboss. Any idea? Have they given anything? Any idea from your side? Pattern. Pattern. I'm talking about pattern, guys. Guys, yes, you can talk. Munmun. Any idea? No, no idea. They have not given. So I think they are going to stick to the old pattern. I feel. I hope so. They will not change much. Okay. Munmun also doesn't know. Okay. Okay. Fine. So see. Okay. What is motional EMF? No, that is what we will discuss today. I will try to do, of course, in detail. You check whether everything is clear or not. Okay. Let me start speaking. I'll speak slowly and properly. Okay. See. Uh, we are still inside electromagnetic induction, and you have learned what is this process. Okay. Whenever there's a change of flux, the rate of change of flux is going to set up an induced EMF, and that is going to result in induced current, right? So that is what we're going to discuss again, actually. Okay, today also. Okay, and that topic is your motional EMF. It is induced EMF only, but another name has been given to it. We call it motional EMF. Okay, so see now. Imagine we have a wire. We just keep it like that. Okay, this is a wire. You can imagine. Right now, I'm just drawing it a bit big. Otherwise, we just draw it in a in a form of a line. But I'm just showing you a bit big wire. Okay. Then I'm telling you that in this wire, we are having another set of wire. Okay, this wire, see the closing wire, no, is closing the shape right now. But I'm telling you that we can move this wire, the blue one, we can move. Okay, we can move that. Now, where we can move that, let me show you. All these are made of metals, by the way. Okay, so they have free electrons. Metals are, let's say, conductors, and they have free electrons in them. Okay, so see where can I move this wire? Okay, the wire I can bring it over here. That means move towards the left. The wire I can bring it somewhere here also. That means I can move it towards the right also. So that's how we can move this wire right now onto that green wire. Okay, so that is what we can do. I'm telling you that. Okay, so now see, I'm going to take this whole setup and I'm going to place it in a magnetic field. So I'm going to draw a magnetic field now. Okay, check whether you are clear with how am I drawing the magnetic field. See, I'm drawing the crosses so you can understand, obviously, right? The magnetic field is entering inside the screen. I'm repeating again, the magnetic field is entering inside the screen. If I ask you where is the north pole, your answer is the north pole must be above the screen, the south pole must be inside the screen. I'm repeating again. Okay, I've drawn crosses. Crosses means the arrow is going inside, arrow is going inside means magnetic field is directed inside, and magnetic field is always directed, right, from where to where. The lines are always directed from north pole to south pole. So since these arrows are entering inside, there is a north pole above the screen. Yes, yes, Noel. So there's a north pole above the screen and there's a south pole inside the screen. Okay. Now all of you check and tell me whether you agree with me or not. Okay, see. So right now we have this rectangular frame, right, which is a wire. Check what is going to happen now. Okay. See. I'm going to take this wire, the blue wire, towards the right. Let me just do that. Okay. So if I take this blue wire towards the right, the new position of the blue wire will be this. See, the blue wire will not be there anymore. Okay, the blue wire will be somewhere here. Okay, new position, right? Okay, initially the blue wire was somewhere here. Okay, so now I've taken the blue wire somewhere there, right? You can easily tell me that the area now inside this coil, right? I can call it a rectangular coil also. I can tell you that the area has increased. Not only that, I can also tell you that the flux, if you calculate now through this rectangular coil, the flux will be large, okay? Because area increases, of course, no problem, right? If the area increases, the flux, right? The number of lines passing through this coil, right? The coil, let me show you again. This is the coil I'm talking about. This is the coil right now. When I move that rectangular, not rectangular, that one piece, right? That we have this piece to the right, the area increases and flux through this whole rectangular coil that I have, I can call it a circuit also, the flux increases, right? So there's a change of flux. Please remember that, okay? I could have even done this, see. I could have taken this blue wire that I have, I could have taken it and displayed to the left, right? Then the amount of area that I'll have is only this much. That means I have decreased the area, okay? So we have this option, I told you, we can take the blue wire to the left or the right. Right now I'm taking it to the right, okay? So this is the new position. Let me show you again. This is the new position. Under this new position we have more area, so the flux has increased. That is what I'm trying to tell you right now, okay? Once the flux increases, I can tell you that there's a rate of change of flux. And whenever there's a rate of change of flux, right? If I have a conductor in that region where there's a change of flux, what is going to happen? Induced EMF will be produced in the coil. So right now I'm talking about that, okay? So I've moved this portion of this coil and that has resulted in the change of magnetic flux. And because of this change of magnetic flux, induced EMF will be produced in this rectangular coil, okay? Now, let me ask you, okay? Think about it and give me an answer. I'm going to ask it slowly, but let's try to be very much clear, okay? Uh, if I take this blue wire towards the right, there's increase of flux, okay? This whole surface that I have right now exposed to the magnetic field, okay? What is this face going to feel? Is it going to feel the north pole above it or not? Yes, it is going to feel the north pole above it, right? Because the magnetic field is directed from north pole to south pole. Above we have north pole, below we have south pole. So if I shift this coil, this portion of this wire from here to here, will this whole area feel the north pole or it's going to feel more and more north pole? That is my question. If you did not understand, I'll ask you again. This is the magnetic field entering inside this screen. I'm telling you that we have a rectangular coil, no, a frame like this, okay? Can I also give you one more information? I'm also going to have another wire which is going to close this figure. All these are conductors, they are metals. And I told you that if I ask you what is the flux is through this much area because there's a closed figure, no? So we can calculate the flux from that figure, okay? But now I'm telling you that I am not having this portion here, that blue wire, but I have it somewhere here. That I have moved it, okay? That I've moved it from here to here. So you are going to tell me, are we experiencing or the coil will have same flux or larger flux? Simple question. First answer me that, then I'll ask you another question. Yes, yes, guys, are you
So
here?
the little flux.
Larger flux. Okay, so that is quite obvious because flux will depend on the area. So larger flux. Okay. Now you tell me, is this face, right? This face that I'm talking about, okay? Is it facing the north pole or not? Yes, it is facing the north pole because what is just above the screen? Above the screen we have a north pole. So it is facing the north pole, okay? So as I have moved the coil, not coil, this portion from here to here, right? Okay. Is this face facing same magnetic field or same north pole, or it is going to feel more and more north pole? What is happening here? That is what I'm asking. Is going to face the north pole or more and more north pole? That is what I'm asking. More and more north pole. Okay, Arjun is right on that, but others, are you understanding what I'm saying? Okay, Geek of God is also there. Okay, Shiro is clear with that. Okay, so now you tell me just directly, what kind of pole should be developed in this wire, in this face? A north pole or south pole? Yes, yes. North pole or south pole? This phase is according to this, okay? When this wire is pushed away, right? Okay, like that. We have more area. This phase is facing more and more north pole, right? So the induced current should be developed in such a way, right? Because there's a change of flux. Induced current should be developed in such a way it will try to oppose the increase of north pole, right? So it doesn't like the north pole, okay? So it's going to generate which pole here? It's going to generate which pole? A north pole. Are you okay with this? because this is the only thing actually, and after that motional EMF is very easy. Okay, Shiro is clear with that. What about others?
Yes, sir.
Arjun is clear, Shiro is clear. Pratisha, are you getting me? Pratisha. Okay, Pratisha is fine with that. Lisa, Munmun is also clear. Good. Okay, Lisa, what about Lisa? Lisa. Okay, Lisa doesn't want to talk. Okay, fine. Okay, now say. So as a result, if a north pole has to be developed, that means the current should flow in this direction. So this red arrows that I'm showing you, okay, it is nothing but induced current that is going to be developed in this entire frame, and that is our induced EMF, or let's say induced current being developed. That means we have some EMF being developed in this entire circuit that we have. Okay, let me show you another case very quickly, and I'll show you in one more way how to talk about this situation right now. Okay, but I think you got me what I'm trying to say. Imagine I have the same rectangular frame like that, and then I have this wire, right, which can slide. No, now I'm telling you that I'll slide this blue wire inward, okay, like that. So automatically it will reach somewhere here, and you can tell me, right, now the amount of area enclosed is this much. So if the amount of area enclosed is becoming smaller and smaller, right? So you tell me now, what is above this face? What is above this face? What is above this face? A north pole or south pole? A north pole, right? So this entire face, what do you think? Is facing more and more north pole, or is facing less and less north pole? Is facing less and less north pole, because the entire area is getting reduced. Okay. As a result of which, you tell me, okay, what kind of polarity will it develop? Will it oppose the north pole, or it will not oppose the north pole? That is my question. Because the entire area is getting reduced. That means it's facing less and less north pole. So it is not going to, okay, it is not going to develop another north pole, but it is going to develop which one? It's going to develop a south pole, because it was facing less and less north pole. It is going to develop a south pole. Okay, I think you got the idea what I'm trying to tell you here. If it has to develop a south pole, then the current will rotate, or not rotate, but move in clockwise direction. Okay, so again I'm telling you what is happening here. Because of the motion of this conductor, right, I'm repeating again, because of this motion of this conductor, which I brought from here to here, right, a current is generated, and that current is called induced current, and that EMF that we are generating right now, we call it induced EMF. I'm going to show you the direction of EMF. How do we talk about that? But that is what is your motional EMF is. Okay, so here check, I'm just writing a definition of that, then I'll proceed with that. Okay, so see, when a conducting rod, means a conductor, is moved through a constant magnetic field, an EMF is induced in the rod, or the wire, and that EMF that is induced because of the motion of this wire, right, we are going to start calling it motional EMF. Okay, so that is what is your motional EMF is. Now I'll show you in another way, and you all decide whether you agree or not. Okay, so I'm going to talk about this one. See, before I proceed, let me remind you, if there is a magnetic field, okay, let me use Fleming's left hand rule. Okay, this is our left hand rule, right? Okay, this is the direction of force experienced by the charged particle. If this is the direction of the magnetic field, force field current, right, FBI, okay, and this is the direction of current, right? Okay, you know when to use it. Okay, let me tell you when to use it. F represents force on a charged particle, B represents the magnetic field experienced by the charged particle, okay, and I represents the direction in which the charged particle is going to give us current, no, okay, or where it is moving. Okay, now try to understand. I'm going to bring this concept somewhere here in the same picture that I've drawn earlier. Okay, let's try to be clear it at once, okay, properly, huh? So I'm just taking up some time. I've drawn the same magnetic field, okay, inside the plane of the screen, and then I'm going to draw again that green line and blue line. Okay, so green is again is a conductor, you can check. Okay, even the blue is a conductor, so let me just do that. Okay, now it's a very tricky idea, okay, to explain, so let me just try it. See, this whole thing is a conductor, everything is a conductor here, so I'm going to get free electrons. So I'm drawing a free electron, free electron, free electron, all these are free electrons. Okay, now uh, the moment, just try to understand these free electrons, okay, averagely in this direction and in this direction, right, the average velocity is zero, average value, because you know, right, because these free electrons are moving in random directions, so the average velocity upwards or downwards in all the direction is zero, okay. But imagine, okay, imagine I am taking this whole rod to the right. If I take the whole rod to the right, I'm repeating again, okay. If I take the whole rod to the right, it appears if all these electrons are moving to the right. All in this rod, okay, not here, not, I'm not talking about that. In this particular blue rod that I'm talking about, okay. So if I move it towards the right, right, the whole blue rod, all the electrons, they appear to move to the right, okay, and that means they have some velocity to the right. Up and down right now their velocity is zero, okay. So see, I'm going to write the velocity of the electrons. Velocity of the electrons is towards the right. Okay, now check. Uh, if the velocity of the electrons is towards the right, okay, since I'm going to apply this, okay, just check. I'm going to apply this. If the electrons they move to the right, okay, I'm not talking about induced current, okay, I'm talking about the real current right now, okay. Induced current I'll show you in a while, huh? So if the electrons are moving to the right, then the current due to the electrons will be towards the left. So I can apply this Fleming's left hand rule, okay? And when I apply this Fleming's left hand rule, I'll get the direction of force in which the electrons will be affected. So I'm going to do that right now. Okay, so you also have to try along with me, okay? You have to take out your left hand. I think by now you know how to take out your left hand, okay? You have to place your middle finger, I'm telling you again, to the left, because electrons are moving to the right. The current, because of the motion of the electrons, right, which is to the right, the real current I'm talking about will be towards the left. So you have to take the middle finger of your left hand and it should point towards the left, okay. And then if I ask you, the pointing finger, right, the second finger, okay, not the middle finger but the second finger, which is the pointing finger, should point inside the screen. I hope you are getting me, okay. So let me just try to do that, draw that. So you have your left hand where the middle finger is pointing to the left and your pointing finger of your left hand is pointing inside. The diagram should look like this, okay. See, the middle finger, this is what I'm drawing, okay. The middle finger of your left hand should point in this direction. The thumb right now, okay, I'm drawing the thumb, okay. All of your thumb should look like this right now. The thumb should point down and the second finger, okay, second finger is inside, okay, which I'm not able to draw of course right now, okay, very difficult for me to draw. And this is how it should look, okay. So see, my diagram is very bad, but still, okay. So this is your second finger, not second finger, wait a minute, middle finger, okay. The middle finger should point in, how am I drawing? The middle finger should point here. The other two fingers are just curling like that, okay. These are your other two fingers. I am not sure whether you are getting me or not, okay. Very difficult diagram for me to draw. So this is the direction of the current, as I told you, right. The pointing finger, the thumb should point. The thumb, you will notice, okay, it is pointing down. Let me just try to on my camera and just let me show you, okay, very quickly. Let me try to do that. So your finger should look like somewhat like this. Why my mid? This is the middle finger, okay. This middle finger is pointing to the left because the whole rod is going to the right, okay. Check my middle finger, huh. This is the middle finger is going to the left. And why is it so? Because your whole rod is going to the right, okay. And the electrons are going to the right. That means current due to electrons will be to the left. The middle finger is going to the left. Why my thumb is pointing? Sorry, not thumb. This finger. Check now, okay. This finger is a pointing finger is entering inside the screen. Automatically, my thumb should point down like that. So your diagram of your left hand should be like that right now. Okay, please keep it like that, okay. So I hope you are getting me right now. Automatically your thumb will be pointing down, okay. So just check. If your thumb is pointing down, right, if your thumb is pointing down, that means the electrons are forced to go down, because we are finding the direction of force on the electron, okay. And I can easily tell you now, if the electrons are forced to go down, right, what will be the direction of induced current? The direction of induced current will be this, because wherever the electrons move now, are forced to move now, there's the direction of induced current. That's why the induced current is going to go up like this. That's why, right, we get all these electrons, okay, because these electrons will force other electrons also, okay, to move in this direction. That's why we get this kind of diagram right now, okay. It is like anti-clockwise. That's why I told you we develop a north pole, okay. I do not know whether you have understood or not this, but I tried, okay, to explain you this. Are you okay with this, what I have done just now? I'm using Fleming's left hand rule. Fleming's left hand rule. Left hand rule. Okay, Shiro did not understand. Okay, I knew it. Okay, you will not understand. Okay, some of you will not understand. Okay, let me try again. I have this magnetic field. All of you are clear with magnetic field? I told you we are going to take a rod here. That is, I think these points are clear. Then I told you I'm going to take a bar here. That bar, I'm going to move it to the right. Till here is clear, I think, no? I think. Okay. So, if I move the whole bar to the right, tell me what happens to the electrons. All these electrons in this blue bar, right? They're going to go to the right. If the electrons are going to the right, do you agree with me? They are going to give me a current to the left or not? Okay, so electrons are giving us current to the left. Okay, fine. So the current, which I should say, right, is the opposite of the direction of velocity. The current is to the left, okay, due to this electrons, no? Okay, so I'm going to now find in which directions the electrons are going to give us induced current, okay. For that induced current, the electrons have to move in the circuit. I want the induced current to be developed in this whole circuit. Okay, so obviously, right now these electrons are not moving in the circuit, they're just moving left and right. Okay, so I'm going to apply my Fleming's left hand rule. According to Fleming's left hand rule, right, the thumb should point in the direction of force F, right? The second finger, right, pointing finger should point in the direction of B, right, FB, that means magnetic field, and the middle finger should point in the direction of current. Then the rest two fingers are curled like that, right? This is how you take out your stretch out your left hand, no? Force, field, and current, okay? So all of you try to put the field right inside the screen. That means this second finger should be pointing inside the screen. So you take out your left hand and point on the screen, no? Point towards the screen, inside, okay? Not out of the screen, inside the screen, no? This middle finger should point to the left. Can you understand? The middle finger should point to the left, because that is where, according to motion of these electrons which are to the right, the current will be towards the left, no? Right now, okay, not the whole current in the whole circuit, but the current that is going to generate for some short time, very short time, okay, that is towards the left, because the electrons are moving to the right. I'm moving the whole bar to the right, okay. Automatically you will see your thumb is pointing down. If your thumb is pointing down, the thumb represents the direction of force. That means all these electrons that I have here, right, will be forced to move down. And if these electrons are forced to move down, okay, that means we are getting current, okay. In this coil we are going to get a current in this direction, that is your anti-clockwise direction. Now is it okay? Are you clear with this, or is your problem something different? You can ask me, Shiro, yes, you can speak also. So you guys have to tell me, is the problem okay, or like did you understand or not? Still not clear, maybe, no? Clear, okay. For Shiro it is clear. What about others? Others also may have problem, okay, because it's not so simple, no? It doesn't look so simple actually. Okay, but this is how you actually have to talk. Okay, Malam is clear, Arjun is clear. Okay, fine. Then I think I can proceed. Okay, so at least some of you have cleared your doubts because Shiro has asked the question. No, okay. Now say, what we are going to do now is we are going to apply a formula. Okay, that is going to give us the EMF. Okay, now to talk about EMF, let me just try to remove some confusion now. Okay, basically students, they have this confusion. Just give me small time and I will tell you what is going on. See, I told you just now, I'm taking this blue bar, I'm moving to the right, and this is the direction of your magnetic field. Okay, this blue bar right now is going to act like a battery for us. Please remember that. It is going to behave like a battery. It's going to behave like it has some EMF. Let me tell you why. Because just now you saw, right, the electrons were moving down. The current was going up, but the electrons inside this blue bar were going down, right? That means if the electrons are going down, that means this side becomes negative and this side becomes positive. So this is how you give the positive and negative of this for this rod, which is going to behave like your battery. Okay, I hope you are getting me what I'm trying to say, because the electrons are moving. Okay, electrons are going down here. That means they are going to accumulate here. Means what? They are going to have more negative charge in that end, and this will have positive end. No, so automatically you can see the current will still go from here as positive, from positive towards that other end. No, this is what is going on. Okay, so when you read the notes again, I think it will be more clear. Okay, but for the time being, I think we are doing fine. Now we are going to find, okay, what is the formula for the EMF that is going to be generated here. So that is what we are going to do. So I'm just going to do it very quickly. Just check. First of all, I'm writing the formula for force on those electrons, or let's say on those charges. Okay, the formula for on the charges is simply your FQVB, right? Because you know the formula is F equals to Q V cross B. Right now I'm not mentioning electron or protons or whatever, I'm just writing for charges. So right now I have this formula. Okay, automatically you can check, right? Magnetic field is inside the screen and the rod is taken to the right and they are perpendicular. No, the rod is on the screen, so they are perpendicular. So automatically I'm going to get QVB sine of 90-degree angle between the velocity of the electrons, which is to the right. When I move it to the right, it is towards the right, and the magnetic field is inside the screen, so angle definitely is going to be 90-degree. Okay, I hope you have visualized that. That means the force on the charges that I'm talking about, individual charges, is VB. Okay, or let's say on all the charges also we can talk like that also. Okay, so this is the force. Okay, now check. If you remember the definition of work done, the definition of work done is what? The definition of work done is how much force is applied on the charges and how much displacement they undergo, right? So if you look at this rod right now, the displacement of the charges that I'm talking about is from here to here. Okay, that is for electrons. If I take a positive charge, it will be from Q to P. Right now in this derivation, I'm writing from Q to P. But if you look at really the electrons are getting displaced from P end of the conductor towards the Q end of the conductor. Okay, and this length of this conductor, I'm taking it L, right? So the displacement of the charges is L. That's why when I calculate the work done in moving those charges, I have to write how much force they are experiencing and what is the displacement. When I do that, I'm simply going to use QVB in place of force, and the displacement is simply how much? L, right? Okay, so this is the work done. Now why am I calculating the work done? Because you know the definition of potential, if you remember, is simply work done per coulomb of charge, per unit charge. Okay, so I'm just going to do that now. I'm writing EMF, or the voltage, must be equal to work done per unit charge. The voltage, or V or E, right, is simply work done by charge. So this is the work done. You can check. This is the charge. Charge and charge gets cancelled. So the amount of induced EMF will be simply VBL, or we can write BLV also. Okay, so this is the amount of induced EMF produced, let me tell you, in this rod, which has a length of L. Please remember that this L is the length of the rod. This V is the velocity of the rod with which we are moving the rod. Okay, if I move the rod, right, the rod, if I move towards the right with a very high velocity, we are going to generate, we can generate a lot of EMF. And if we have a larger magnetic field, we can generate a lot of EMF. Okay, so this is the formula to calculate induced EMF, of course, produced due to motion of that rod, okay, which is connected to the whole circuit. Okay, now let me just show you one very important and very easy rule to understand the direction of induced current during this motional EMF picture. Okay, so we have a rule to know the direction. Okay, we know the induced current direction already actually, but let me still tell you properly how to talk about this direction. Okay, for that we have a rule called Fleming's right hand rule. Please remember now. When will you use Fleming's right hand rule? We are going to use Fleming's right hand rule to know the direction of induced current whenever we are talking about motional EMF. Okay, and see how it goes. See, I'm going to take my right hand. This is my right hand. This is the second finger. This is the middle finger. I'm going to stretch it out. These are the other two fingers. You can check. Okay, my diagram is very good now. You can understand. I hope so. This thumb should point not in the force direction. Okay, but actually the motion now. Wherever the rod is going to move, you point your thumb in that direction. So if the rod is moving to the left, you have to place your right hand and the thumb should point to the right. Okay, and if the rod is moving to the left, okay, so the thumb should point to the left. That is the meaning of this thumb here right now. Okay, This second finger, again, if you check, it is pointing towards the field, magnetic field. Wherever the third pointing finger, right, the middle finger, wherever it is going to point, that will be the direction of induced current. So that is what I'm going to show you right now. Okay. So I think it will be clear for you when I show you. Just check here. I have this picture again, as you can see, and I'm showing an easy way actually, okay, to know the direction of induced current. See, so this is the magnetic field. Again, you can understand the magnetic field is inside the copy. That's why I've drawn cross. Let's apply this rule, okay, that I've written just now. This one. Copy. Let me just paste it over here. Give me 1 second. Okay. Okay. Keep a track of what, which is what. Okay. What is the direction of what and what. Okay. See. Okay. You have to stretch your right hand like this, as I told you. Let's take this blue rod to the right. We'll take the blue rod to the right. Okay. And you know, right? Already a north pole will be developed. You've already told me the answer. Okay. Because area is getting bigger and bigger. This face is going to feel more and more north pole. So it wants to oppose that. And that's why we are going to generate a north pole here. Okay. So how to apply this now, no? To know the direction of induced current, check. This thumb you should point in this direction of your right hand. Thumb. Okay. The middle finger that you have, okay, should point in the direction of the field. Middle finger inside the screen. Middle finger should be inside the screen, okay. Middle, not finger, okay, finger. Should be inside the screen. Because the field is inside the screen, okay. So when I do that, the thumb is pointing to the right, the middle finger is inside the screen. You tell me where is your second finger. Wherever the second finger points, it is the direction of current, okay. So you have to tell me where is the second finger, not second finger, sorry, middle finger pointing. That is my question. Where is the middle finger pointing? The second finger, sorry, not second, I wrote here wrong. Not middle finger, this one, sorry, my bad. Okay. The second finger should point inside the screen. The second finger inside the screen. Okay, so I'm asking you again. Okay, please take out your right hand. Take the thumb on the right hand side. Right, it should point to the right. The thumb should point to the right. The second finger should be pointing inside the screen. Where is the middle finger pointing, guys? It is pointing up or down. Please tell me. What do you see? Upwards. Yes, Arjun has got it. Okay.
Upwards.
Upwards. Yes, upwards. Okay. So this is the rule that you have to use. Okay, to know the direction of induced current. So just now you saw it is upwards. Those who are not getting it, please ask me right now only. Okay. So this confusion should not go on with you. Okay. Should not move on. Okay. Right now it should be removed right now only. So if the current is going to be upwards in this rod, that means the current throughout this will look like this, and definitely it's like generating a what pole? It is generating a north pole. Okay, guys, can I say it is okay? Is it okay? Yes, I can see 2 to Shiro here. I don't know why. Okay, Arjun is clear with that. Arjun
So
understand.
even
Okay.
me.
Yes, sir.
Okay, even yeah, Shiro understood. Very good. Okay. What about Shishan is clear? Malam is clear. Very nice. Okay. Then I think I can proceed now.
So
Anybody
why
else
is
down?
that
Just a bit.
too, sir?
Yeah, I don't know. Shiro is connected two times, no problem. Okay, Aniket is also there. Okay,
Yes,
so
sir.
see. Okay, I hope you got me what I'm trying to say. So, guys, if I ask you how do you find the direction of induced current, please always use which rule, guys? You are going to use Fleming's right hand rule. Okay, so this is what you're going to do. Okay. Now there is this problem. Let's do it right now. I think it's an NCRT problem. Okay, and we are going to do it right now, and it's a very nice problem. Okay, we'll take up some time, no problem. We can take 5 minutes for this problem also, but let's try to do it properly, huh? Okay, check now. It's based on this problem only that we have done just now. Don't forget, there's a formula for calculating motional EMF, that is BLV. B means magnetic field, L means length of the rod that we are moving, V is the velocity with which we are moving the rod. Okay, so that is what we have. Now check. This question is a very nice question, okay, but many things are there, so we'll try to go slowly. Each and every point, let me try to make it clear. Okay, say a horizontal straight wire 10 meter long extending from east to west. check. You can understand I've taken a wire here. The green one is the wire. Okay. If you look at my diagram, I've kept the wire horizontally and I've kept it not like this, not vertically, right? I've kept it horizontally. Okay. It is extending from west to east. No, that means it is going from east to west or west to east. Same thing. Okay. So it is in this direction from west to east. Okay. It is not here like that. It is not here like that, right? It is not from south to north or north to somewhere else and so on. Okay. So that's your question right now. Let me proceed with the question. Okay. I hope you understand till here. The question says this wire that I'm talking about, okay, is falling with a speed of 5 meters per second. You can understand the diagram. The whole wire, right, is falling with a speed. Of course, it's falling down, right? They cannot fall up, okay? So it's falling down with a speed of 5 meters per second, okay? At right angle to the horizontal component of the magnetic field. Now, this is very important. See, at right angles to the horizontal component of the Earth's magnetic field. Okay, check now. Where will you get look at this B here that I've drawn here. Okay, that is the magnetic field I'm trying to represent. Why am I calling it horizontal? Check, guys. Look and tell me. Okay, what do you think? This BH that I've written here, have I drawn it vertically or have I drawn it horizontally? That's the first question. Have I drawn it horizontally or vertically? What do you think? If this is you, this is a mountain. Horizontally, yes. Okay, this is a mountain. You could have that scale, right, which is pointing towards the mountain. Let's say this is north, this is south, east and west. You cannot hold the compass like that, okay, and say that that is north. This is not north. Definitely not. Okay. So your whole north is southwest. Are these directions vertical directions or they are horizontal directions? Northeast, west, south, they are horizontal directions. Please be clear, okay? It is not, don't think upwards, you look upwards and say that is not. No, that is wrong, okay? So now check, okay? Please tell me, guys, you tell me, are you clear that I'm drawing this magnetic field, right? And why am I drawing towards the north? Because the magnetic field will always point towards the north. Because here you have which one? Here you have magnetic south pole. If you remember, I told you near the north pole, right? What do you get? You get magnetic south pole. SOUTH, south pole. And near the south pole, right, of the compass, you get what? Magnetic. Which pole do you get? You get magnetic north pole. Okay, that's why you see I've not drawn the arrow somewhere here. Why I did not draw the arrow here? Because magnetic field of the earth cannot be somewhere here. Okay, because the south pole is here, the north pole is here. How can the magnetic field be pointing somewhere there? No, the magnetic field has to point in the direction of which pole? Towards the north and the south. Okay, and you can understand already, right? What is this called? Will I call it horizontal or vertical? What do you think? The BH that I'm drawing here, will I call it horizontal component of the Earth's magnetic field or vertical component of the Earth's magnetic field? Yes, guys, yes, hurry up, hurry up. We have to call it horizontal, right? Because it's lying in the horizontal plane right now. Okay, I hope you got my point. Okay, that's why when I draw this diagram, the diagram looks like that. Okay, now there are so many things that they're talking about. See, they've also given us the value of horizontal component of Earth's magnetic field. If I'm talking about vertical component, no, would have drawn it something like that. Okay, so that would be the vertical component. But don't worry, we are not talking about that. So yes, I was talking about the value they have given 0.30 10 to the power minus 4 Weber per meter square. That is like Tesla only. Okay, so that is the value of your magnetic field given. The length of this rod has been given, okay, and the velocity with which it is falling, it is also given. Our job is simply to calculate what is the value of the EMF induced. Okay, do you agree with me it is problem from motional EMF or not? Whenever a rod is going to fall, one end of the rod becomes positive and one end of the rod becomes negative, no, because the current will start flowing, electrons will be drifted in some directions. Okay, that's why we develop motional EMF right now. And the expression for motional EMF is what? You take the magnetic field, you take the length, and you multiply with velocity. And that is what we are doing right now. See. So see, we got it easily. Okay. I hope you have understood the question. Because the wire, we need a magnetic field. Okay. And the wire was falling in a magnetic field. Okay. Shiro is clear about this. 1, 2 responses. Then I will proceed to the next question. That is number B, of course. What is the direction of, okay, so Rishita is clear. Okay, fine, I'll proceed. Okay, what is the direction of EMF? EMF direction we are going to talk about, no? So let's do that. Okay, so see, uh, how do you know the direction of current? Let's talk about direction of current. Okay, so guys, you have to tell me which rule should I use. You are going to tell me we should use Fleming's right hand. Right hand. That is the rule I'm going to use. Okay, Fleming's right hand. Okay, how do we use Fleming's right hand? The thumb should point in the direction of motion. You can already understand the thumb should point down, right? Because that's the motion of this rod. Okay. Then the second finger should be pointing inside the screen, right? All of you, are you getting me? The second finger should point inside the screen. Your second finger means this finger, okay? And your third finger, right, wherever it is pointing. The third finger, wherever it is pointing, that's the direction of induced current. Okay, so guys, you are going to tell me right now, okay? Apply this, please apply this. Second finger pointing inside the screen, thumb pointing down because motion is down. Where do you find your middle finger? Where's your middle finger? Yes, waiting for some answers. Thumb is pointing down, second finger is inside. Where's your middle finger pointing? To the right or the left? That is my question. Good, good. Shiro has got it. It is pointing to the right. Please.
To the
Yeah.
right.
To the right, to the right. Aniket is also back. Okay, yes, to the right. Is it clear for all of you guys? Iba, are you getting me what I'm doing?
Yes, sir, it's clear.
Okay, okay. What about Iba? Iba? Okay, Iba is also clear with this. Okay, I think I can proceed then. Okay. Okay, so that's why if the direction of induced current, if it is to the right, that means this side must be positive and this side must be negative, no? Right? Because the current is going from west to east. Okay, to the right means west to east. That means this west must be positive and east must be negative. Okay, so direction of induced current is from where to where? It is from west to east. So we have answered the second question also. Okay, which end of the wire is at higher potential? You can easily tell me, right? Which one is at higher potential? The west must be at higher potential and the east must be at lower potential. Okay, so this is a very typical problem, okay, that they have given. So whenever they give you this kind of question, right, with a rod or something that is moving in a magnetic field, apply motional EMF rules, okay, and that is what you're going to do. Okay, I hope this part is clear. Okay, you guys today joined very late, right? I'm already 8:52. I thought I was doing one more topic. I'll do it, of course. Let's go for your eddy currents, okay, very quickly. I think you have understood this part. So let's go to eddy currents, okay. Eddy currents also they used to ask, huh? I'll put some more questions on motional EMF, okay, in the notes and all. So let me complete eddy currents right now. Nice topic, okay. So we'll do this right now. I hope so. We'll get time, okay. So see, eddy currents is also a result of electromagnetic induction. That means you come and change the flux. The change of flux will produce induced EMF, and of course we'll get induced current, right? This is the same process, but we have a different name for it. It is called eddy currents, okay. It is frozen. My iPad is frozen. It's not moving at all. Okay, now it is moving, I think. Yeah, now it's moving. Okay, now see, okay. Yeah. So what is this? See, I'll give you this example here very quickly. Okay, let's learn the definition of what are eddy currents very quickly. See, I'm taking a bulk solid, bulk metal. Bulk metal means a very big piece of metal. It's not a wire. Check. Okay, it's not a wire. I'm not taking a rod. You can see it's a bulk piece of metal. I'm going to have lots of free electrons in it. So I'm drawing them. Okay, we have a lot of free electrons. No problem with that. Okay, check what am I doing. You will agree to me that I'm bringing the North Pole closer and closer towards this bulk piece of metal. That is what I'm doing, right? So what will happen? The free electrons inside this metal, they will be forced, right? They will be affected by this magnet, because a magnet will produce magnetic field. And of course, when I bring the North Pole closer and closer, right, this whole piece of metal is going to oppose that, okay, and it can oppose that by developing a current. That current should flow in such a way that it will try to oppose the coming of North Pole. This whole metal piece now, okay, is going to say, North Pole, you are coming towards me, I will not let you come towards me, I will oppose you, right? So it has to develop a North Pole in this metal itself, okay, but I'm drawing only on the surface. It is developed throughout the body of the conductor, this whole North Pole, right, which will face this North Pole to oppose the coming of North Pole. it is going to be generated throughout the body of the conductor. Okay, that means the electrons, they are going to give me a current in the anti-clockwise direction. To be more accurate, let me tell you, to be in another way, I'm telling you that the electrons, they start moving in the clockwise direction. The electrons, when they start moving in the clockwise direction, they are going to generate a current in anti-clockwise direction right now. Okay, similarly, let's just check here. Here also see the north pole is going away, right? Check in this diagram, the north pole is going away, right? So electrons, the free electrons inside this conductor, they are going to react to that north pole which is moving away. Okay, so the north pole should not go away, right? They are going to oppose it. Earlier the north pole was coming, they did not allow, the whole body of this conductor did not allow the north pole to come. Now the north pole is going away. The whole body of this conductor will not allow the north pole to go away, right? By developing which pole? By developing a south pole. Okay. Now, in order to develop the south pole, the current that should be induced here should be clockwise current, right? So I'm drawing a clockwise current. You have already learned this idea. Okay. What it means that the electrons are going to start moving in the anti-clockwise direction. They are going to rotate like this, see, anti-clockwise direction. Okay. Now, what happens is that because these electrons are moving in a circular path, okay, throughout the body, no, they don't have a particular path here actually. Okay, don't think only in this path they are going to rotate. No, throughout the body of the conductor they are going to rotate and rotate and rotate in a circular path. Okay, and that's why they are called eddy. Let me tell you what is the meaning of eddy. Eddies are actually circular shaped movement, circular or spherical, not spherical, let's say spiral movement of water. Let me just give me 1 second, let me write and let me tell you. Okay, this is a sink. You know what's a sink, no, guys? I think you know, right? Sink. Early morning, you brush your teeth. You have a sink. You have water here, no? See? How does the water falls down this sink? Does it just go straight?
So in a spiral.
In a spiral way, no? Like circle and circle and circle. Yeah, spirally, right? They spirally, they go down, okay? Same thing happens with these electrons also, okay? By the way, this kind of motion is called eddy, okay? We call them eddies. I think you understand, right? Eddies means this motion is called eddies, okay? If even the electrons right now in this metal piece, they rotate like that, just like the water in this sink, they rotate. No, even the electrons, they rotate this way. Okay, that's why we call them here what currents? We call them eddy currents. Another name for this current is this one. Okay, see, we call them Foucault current. Okay, Foucault is name of some scientist who discovered this phenomenon. Okay, so we call it Foucault current. Okay, now check. Now the important part is this. See, the important part is eddy currents are always developed to oppose the change in magnetic flux, just like your other currents that we have seen earlier. No, other thing in electromagnetic induction we have seen. Okay, and the direction of eddy currents is also given by which law? Lenz's law. So we have just applied Lenz's law again. You can check we have done that. Okay, now see, but okay, now important point is this: when the magnet we brought it closer and closer, right? Because the north pole is developed, it does not let this magnet come closer and closer, means much closer. Okay, and when the magnet wants to go away, this south pole is developed here, and again this south pole which is developed by this bulk piece does not want this north pole to go away, right? So what do you think? It is helping the motion or it is destroying the motion? What do you think? When the north pole was coming and coming, right? We developed a north pole, right? And did not allow the north pole to come so fast. We have reduced the speed of the north pole actually by developing another north pole here. Okay, and when the north pole was going away, let's say this metal develops what? Develops the south pole and does not let this north pole go away very fast, right? So what is going to happen? Tell me, guys. Is the motion of this north pole and north pole, the whole magnet going away and coming to the coming to the metal piece? Are we helping this motion or we are destroying the motion? What do you think? Yes. Imagine this is Kirshan running towards this metal piece, running with a speed of 40 meters per second. Okay, what will the metal piece do? Metal piece also will develop. Metal piece also will develop north pole. Now, what do you think? As Kishan is coming closer and closer and closer, if Kishan is coming closer and closer and closer, okay, what do you think? Will Kishan still move with a speed of 40 meters per second, or the speed will be reduced? The speed will be
So speed will be reduced
reduced. Very good, reduced. Okay, and of course, Kishan
due
is
to repulsion.
due to repulsion. Yes. Okay. Now look at this. Now Kishan is again north pole, but Kishan is running away. What pole will be generated? Running away with 40 meters per second. What pole will be generated here? South pole, right? because
Yes, sir.
the magnetic piece that doesn't want Krishan to go away, right? So it will develop south pole. Now you tell me, can Krishan go away with a speed of 40 meter per second or cannot go? It will reduce.
Cell reduce.
It reduce. It's going to hold you back. No, that's what's going to happen. That's why see I'm writing here. See, eddy currents they're always going to have a tendency of what? Opposing the relative motion. Okay, there's an experiment also. Okay, I'll show you. I'll tell you what to watch. I'll show. Maybe I'll send you later around 10 o'clock a video. Okay, that you can understand what is going on. No, it's used to retard the motion. Okay, so now check. Okay, that there's a very big disadvantage of eddy currents. See, eddy currents, right? Just now I told you, you have a metal piece and the electrons they are rotating. They're going to keep on going round and round because of the change of flux. No, so there's a change of flux and the electrons they go round and round. See what does it do? Okay, when the electrons they go round and round and round like that, they keep on moving in a given path. If they keep on moving in a given path, they hit other atoms and other electrons on their way continuously. Okay, because of these collisions, a lot of heat is generated. Please remember this. A lot of heat is generated. I'll give an example and then maybe you'll understand. Okay, take a north pole here, take a south pole here. Take a metal piece. Take a metal piece. Okay, make it go through this magnetic field. This metal piece I'm talking about. Let it keep going. Okay, going and coming, going and coming. Let it keep going, coming, keep going and keep coming. Right. So when this metal piece is let to pass this magnetic field again and again, okay, what are you going to generate? You are going to generate this eddy currents, right? Automatically you will see that the temperature of this metal piece is rising. Why the temperature is rising? Because the electrons in this metal piece they keep on start moving round and round and round. They hit and collide with other particles in this metal, right? Okay, they do that. Okay, they do that, and then what happens? When they're continuously colliding with other electrons and other atoms, right? They are going to generate heat. Okay, and the temperature of this metal piece is going to go rise. Okay, that is. I hope you understand what is the meaning of eddy. I think you're clear with eddy currents, guys. Is it okay? Can I say you're clear with eddy currents? I will tell you the question also. What kind of question they come? Okay, they will ask you what are eddy currents. They'll ask you what is the disadvantage of eddy currents, right? Lot of heat generated. I can another way say it is like what loss of energy. Okay, so this is one disadvantage. There's a loss of energy because of production of eddy currents in any electrical device. Okay, where you are using a magnetic field and you have metal pieces near it, right? Some of the electric field in that circuit or electrical device will have develop. Okay, will develop heat also. No, instead of just giving you electric current and electrical energy, right? Some of that will be converted into heat. Okay, so there's a loss of energy actually. It happens with the transformers and also we will talk about that also. But let me tell you some advantages are also there. Okay, so very quickly I'll just talk about one advantage right now. One advantage or let's say application. Okay, very quickly let me do that. Application. Say what is the application? I have a train. These are the wheels of a train. Okay. Uh, wheels of a train, I think you know, right, are not made of rubbers. Okay, they are made of what? Metals. No, metals. Okay. This is a track. This is a track. In this track, okay, let's say I want the train to slow down. Okay, this is a station, no? So I want the train to slow down. What we will do in this track right now that I'm talking about, I'll put magnets. If I put magnets in the track, okay, where I want the train to slow down, what will happen? This is a metal piece, right? This one, check. This is a metal piece. These wheels are all metal piece. Okay, the wheels, all the wheels. Once they reach the track where we have magnets, what will happen to the wheels? You tell me, guys. Will the wheels generate? Because see, the whole wheels are coming towards the magnet, no? That means there's a change of flux in the wheels. Okay, so the wheels are going to generate what currents? The wheels are going to generate eddy currents. The eddy currents will be generated in such a way that the motion of these wheels will be opposed. I hope you understand what I'm saying. Okay, such that the wheels, instead of moving faster and faster, what will happen to them? Please guys tell me now. Will the wheels become faster and faster or will wheels become slower and slower? Yes, the wheels are going to become slower and slower. That's how you are going to, yes, okay, that's how you are going to Break, right? Break the train, okay? Not break the train, but make the train break, no? Okay, I hope you understand my point. So that is what is happening, okay? So these eddy currents are very nice, no? They can even stop a train, no? Stop. We call it, what do we call it? We call it braking. Electromagnetic braking, I think. Electromagnetic braking, we call it, okay? Okay, whatever it is, name is there, you can check and all. But I think you got, you understood one of the application. Uh, yeah, of course, heat is generated, yes. Heat is generated, no problem with that. Heat will be generated. Heat is generated. Don't worry, it will not burn, no, because not that much heat will generate that it will start burning the wheels and all. Okay, so that is not going to happen. Okay, guys, did you understand eddy currents for today? I'm going to stop. Okay, so are you guys clear what I did today? Can I say it's okay?
Yes, sir.
Okay, for Arjun it is clear. For Shiro it is clear. Aiba, I don't know. You joined late or I don't know exactly what is the case. Okay, but I'll do like this. If you have not understood, please check. Okay, the video again. Okay, I'm going to upload, of course, again. So please check. Okay, so I'll just stop for the time being. Okay, we'll meet tomorrow and see. Okay, what I was thinking. No, can we increase the timing a bit? Because see, I want you to start preparing properly for your final exams. Okay, so uh, yeah, I will write in the group. Okay, and yeah, yes.
Sir, I have a request. If you're going to increase the timing for tuition, sir, I think it's better if you start
I did not hear you. Start at what time?
before 8, sir. At
7:30.
least you should start by
Yes,
7:30,
yes,
sir.
yes,
Then
yes. Yes,
that'll be better,
7:30,
sir.
7:30. Exactly 7:30. I'm talking about. Yes, if everybody is okay with that. Okay, so please write in the group. Okay, we are meeting from tomorrow from 7:30 to 9 p.m. so that I start covering more and more things so that later you will not have any problem. Okay, so in between, okay, we'll do some other things also. Okay, Krishan can dance also. We'll get enough time. Okay. So bye guys. Huh? Also for now. Huh? Bye.